Uh, Thank you so much for inviting me. My talk, I think, kind of fits in quite well with the rest of the schedule. So I'll be talking about special Lagrangians from the perspective of Morse theory. And special Lagrangians are a special type of submanifold inside a Calabi-Yau manifold, which we already heard a little bit about. And this will also have some small connections to G2 geometry, which we'll hear more about from Anna later. Okay, so here's the sort of rough outline. These topics I'll kind of go back and forth between 2 and 3 a bit. But essentially, this talk is about an idea which was originally I found in a paper by Donaldson and Siegel called Gauge Theory in Higher Dimensions. And it's just sort of outlined in a paragraph in that paper, and I've kind of expanded on that a lot. And it also kind of builds on the work of my advisor, Alexander Doan, and his collaborators. And it's kind of along the lines of finding invariants for these special kind of manifolds. So what's going to happen is we're going to describe a certain Lagrange multipliers problem, and I'm going to take a finite dimensional analog as kind of inspiration and try to work out the details of that. Okay, so first of all, let's just figure out, or I'll tell you what a special Lagrangian is. So before I tell you that, I have to tell you what a Calabi-Yau is. So a Calabi-Yau manifold is just a manifold that has a complex structure, a Kähler structure, and a holomorphic volume form that satisfies some compatibility conditions. So this constant C here, it's not really that important. It's just some constant and it's chosen so that the real part of this volume form is something called a calibration, which I'll tell you what that is later. For now, I'm going to, all my Calabi-Yau manifolds will always be compact. And in general, I will be interested in only Calabi-Yau threefolds, so real dimension 6. And there are a couple other definitions of this around, and not all of them are exactly equivalent, so you have to be a bit careful. Some special things about Calabi-Yau manifolds is that the Calabi-Yau metric is always Ricci flat. So this is very interesting. And the holonomy of the Calabi-Yau manifold is contained in SUN. So this is an example of manifolds with special holonomy. And this is studying these is the main kind of motivation for what we're doing. Although there's actually other applications that might be possible, but I'm not sure. That's where I'm coming from. Okay, so there was this famous theorem. It used to be called the Calabi conjecture, and it was proved by Yau. And I think I've heard some other people say other people worked on it too. So, but I'm not sure. So generally it's called Yau's theorem or the Calabi conjecture. And basically what it says is that if you have a Kähler manifold and the first Chern class is 0, then there exists a unique Ricci flat metric, which isn't necessarily the same one as the one we started with. And that is Ricci flat. And it's got another Kähler form such that they're contained in the same cohomology class. So this is pretty amazing because this gives us a really kind of easy way to come up with tons of compact Ricci flat examples using algebraic geometry. And prior to this theorem, it was kind of difficult to come up with examples of compact Ricci flat manifolds other than like a torus or something. Calabi-Yau manifolds are also interesting to physicists for reasons I don't particularly understand. In any case, now I'll tell you what a calibration is. So if you've got yourself a Riemannian manifold, then a closed K form on M is called a calibration if you restrict it to any K plane in so like a subspace, okay, so V would be in TXM or something, then that's going to be less than or equal to the volume form on that plane. Right, so then if you have a calibration, you can consider all the calibrated submanifolds whose tangent planes are all calibrated by that form. So why would we even care about calibrated submanifolds? Well, they're very interesting. For one thing, they're volume minimizing in their homology class. And the proof of that is very simple. It's just this one-line thing. And that's very interesting because this calibration condition is a first order PDE, where if you just took if you were looking at minimal surfaces or something, that would be a second order PDE. So of course, not all the minimal submanifolds are calibrated, but generally the calibrated submanifolds, whenever they exist, are very interesting for all kinds of different reasons. Okay, so then we have this fact that if you have a Calabi-Yau manifold, the real part of the holomorphic volume form is basically constructed so that it's a calibrated submanifold. And calibration. And we call those calibrated submanifolds special Lagrangians. So special Lagrangians are literally just the calibrated submanifolds of the real part of the holomorphic volume form. And by the way, you could take the imaginary part or a combination of the two. But for now, I'll just restrict myself to the real part. So I'm not really interested in different phases, but that doesn't really matter. Okay, so this whole idea of calibrated submanifolds was introduced by Harvey and Lawson in a paper, which I forgot to write the year down, but it was a couple decades ago now. So in that paper, they gave this very useful proposition that says that I can think of special Lagrangian submanifolds as any three-dimensional or half-dimensional manifold. So in my case, I'll be focused on complex dimension 3. So any real dimension 3 submanifold admits a calibration if and only if it satisfies these two conditions. So we can just take the symplectic form, and if that restricts to be 0, and then the imaginary part of the volume form also restricts to be 0, then I know it's a special Lagrangian. And that's a bit more useful in terms of computations. Okay, so here's some kind of history about things at least loosely related to this topic and some context. So there's been this sort of long history of people counting interesting objects, usually submanifolds or maybe some special connections that satisfy some special equations, and getting in various different invariants. So this applies to symplectic geometry, a lot of stuff in 4-dimensional and 3-dimensional manifolds, for example, Seiberg-Witten invariants. And then when it comes to these higher dimensional manifolds that have special holonomy, such as Calabi-Yau and G2 manifolds, basically the idea is we'd like to use the special properties of those manifolds to extend gauge theory and this idea of counting things to come up with invariants to 6 and 7 dimensions and maybe even 8 dimensions. So that would be quite exciting. So that's sort of the big goal. So that's basically what I want to do. So I want to, the goal of this project is to come up with some kind of floor theory where the special Lagrangians are kind of generating it. And of course, that's like way in the future, maybe it would take me 10 years or something. So this is just the very tiny first baby steps towards that. So the idea is generally, can we get some special Lagrangian invariants, some invariants that come from special Lagrangians? Okay, so let's just go into a little bit more details about sort of why that might be a good idea. So in addition to calibrations, there's this other kind of perspective you could take, and that's the perspective of stable forms. So this was introduced by, I think, Hitchin in a paper called Special Metrics and Stable Forms. I have this written down somewhere. So basically, in that paper, he calls a form stable if it has a GLNR orbit. So GLNR can act on any P form, and just by pulling back. And so then we look at the ones which have open orbits. So literally the orbit is just open. And they don't always exist, and they're generally harder to find in the higher dimensions, but when they do exist, they're usually something we're familiar with. So here's some facts about stable forms. If you've got a stable P form, then you also have a G structure on your manifold. So, and the G is going to be the stabilizer of alpha. So for example, a symplectic form is a stable 2 form, and then we get a symplectic structure from that. Also, if we have a stable P form, we also have stable N minus P forms. And one reason for that is that each stable form preserves a volume element. So for the symplectic form, it's the usual symplectic, this combination of omega where you get this volume. I'll show you some examples of that later. But and it's basically just because the stabilizer is an SLN. So that's why it preserves a volume element. So then you can get this sort of dual, which is very much like a Hodge star, but it's not. So it's we call it a Hitchin dual. And they're related to special holonomy. And so they're related to special holonomy in the following way. So if I have a stable form on a manifold, then I can define, like, for example, a G2 structure, that would be a stable 3 form on a 7 manifold. Then saying that it's torsion-free, or that the holonomy of the corresponding metric is actually contained in G2, is equivalent to putting conditions on the stable forms. So this is kind of a very computationally convenient way to talk about these special structures. Okay, so 6 dimensions, 6 real dimensions, that is quite special because we've got a lot of stable forms. So there are stable 2 forms, there are stable 3 forms, and there are also stable 4 forms. So the stabilizer, there are 2 types of stable 3 forms. We've got one with stabilizer SL3C and one with stabilizer SL3R cross SL3R. I'm not going to talk about these ones. So we just sort of arbitrarily call one of those positive and one of them negative, and I like the positive ones. So I can explicitly write down what the Hitchin duals are of these stable forms. So here, omega will always be a 2 form, and tau will always be a 4 form, and rho will always be a 3 form throughout the entire talk. So I can explicitly write down what the Hitchin duals are. And then, right, okay, so this is what they are. So this is the sort of context we're going to be looking at. And then because 6 dimensions is so special, these stable forms, I can actually define an SU3 structure on a 6-dimensional manifold in terms of these stable forms. So it's just that an SU3 structure on a manifold M is just a pair of stable forms that satisfy some algebraic conditions. Okay, also G2 structures come from this. Now here's the idea from Donaldson and Siegel. If I have a 6 manifold that has a closed SU3 structure, so that just means these forms are closed. If their duals were also closed, then it would be Calabi-Yau, but it's not exactly Calabi-Yau. Then I can define a functional, which is written down here, which is going to act on, roughly speaking, it's going to eat 3-dimensional submanifolds and spit out a number. So the reason I say roughly speaking is because what we want to do is integrate the 4 form over cobordisms from where the ends are 2 3-dimensional submanifolds. So actually this is only defined on, for example, the covering space of all embeddings or something. But roughly speaking, if you fix a submanifold or an embedded submanifold and then you have a nearby one, you can integrate that 4 form over a 4-dimensional manifold connecting the 2. Okay, so we've used our 4 form from our SE3 structure. We should also use the 3 form. So let's say that C rho is the set of embeddings of my 3 manifold, where the pullback of the 3 form is 0. Then I have a Lagrange multipliers problem. The Lagrange multipliers problem is find the critical points of this functional restricted to this submanifold. So it's a Lagrange multipliers problem in the sense you probably remember from calculus. So here's the Lagrange multipliers theorem. Okay, I'm very short on time, so I'm going to move on. So basically, we can set up a Lagrange multipliers problem, and we can write down a Lagrange functional, which is very much like the Lagrange function from calculus, from the regular Lagrange multipliers problem. And we have this Lagrange multiplier showing up. So in this case, the Lagrange multiplier is going to be a function on the submanifold P, or the embedding of the submanifold, so which is the submanifold. Okay, so our Lagrange multiplier is a function, and we get 2 equations from this when we solve the Lagrange multipliers problem. So we have these 2 equations, which we call the Euler-Lagrange equations. Then, due to that lemma, which we already stated, we can kind of easily see that if lambda here is 0, and I let rho be so if I start out with a Calabi-Yau manifold, and then rho really is the real part of the holomorphic volume form, these special Lagrangians are exactly the solutions to this Lagrange multipliers problem. So that's what motivates us to try to do Morse theory with Lagrange or with special Lagrangians. Okay, but there's a bit of a problem. So it's a theorem of Maclean that if you have a special Lagrangian, the nearby moduli space of special Lagrangians is a smooth manifold of dimension equal to the first Betti number of your special Lagrangian. So that means the critical points of this functional are not isolated. So we really want to move forward with defining this thing, we really want to consider the case where we're not actually in a Calabi-Yau structure. We're in something that's kind of like that. So the lambda is not equal to 0 part is going to be more interesting. Okay, so one thing that I did was wanted to figure out how Morse homology works in the Lagrange multiplier setting. So these people, Schechter and Shu, actually did prove that for a case where you would just have a trivial rank 1 bundle, and I just sort of generalized that to a bundle, and it was very similar to what they did. But so it's kind of interesting because the Morse homology of the Lagrange function, the domain is not compact. So it's a little bit tricky to define what that is, but what you can define it, and it turns out that it's actually equal to the Morse homology of F restricted to this compact submanifold. It's just that the grading is shifted a bit. Okay, so this gives us good motivation to continue working on our problem. So basically, like I said, I have not that much time, so I'll just sort of say what we've been working on, and then I will stop. So it turns out you can see this whole problem from the perspective as a dimensional reduction of a 7-dimensional manifold. And that's really useful because actually in this case, G2 turns out to be a little bit more simple, and you can use that to prove ellipticity and also volume bounds for the critical points and the gradient trajectories. And currently I'm working on some transversality results for this, and that's it. So I'll stop here.
Do we have questions for Emily? Yeah.
Oh, but, okay, I'm not sure what you mean. What do you mean pull? Like, what would the map go from and to?
You have a map between manifolds. If you have a differential form on the ambient manifold, you can just pull back. That's another form.
Yeah, so not in general, although I guess do this because I start out with my 6 manifold and then I go to the G2 cylinder, and then I often pull back the G2 form. So I do use that concept, but not in general.
I see.
Yeah.
Suppose you have a map on the same dimensional manifold, between same dimensional manifolds.
Right.
Would there be any possibility if you have a conformal? Can you say something? Or?
I haven't thought about that at all, but I could think about it.
Yeah,
I don't know curious. Right now. Yeah, I'm not sure.
Thanks. Yeah. Okay. Thank you.
So I have a question about the functional that you was trying to do the Morse theory. Is it known if the Palais-Smell condition hold for your functional?
I don't know. So I do know. So what I can prove is that in the finite dimensional case, let's see, did I write it here somewhere? So in the finite dimensional case, we do have, I can show that the Palais-Smell condition is satisfied by the Lagrange function. So in this finite dimensional case, this Lagrange function satisfies Palais-Smell, but I don't know about the infinite dimensional case yet. So that is one of the things I need to do, is kind of figure out what the analog of this would be for my actual problem.
And for my second question, you talk about the Lagrange multiplier on a constraint variational problem. Is it known whether the constraint is in general non-degenerate to answer the existence of the Lagrange multiplier?
Wait, the constants?
No, the constraint.
Oh, constraints. Oh, if the Lagrange multiplier is non-negative?
No, if the functional is non-degenerate on the constraint to
Oh,
ensure the existence of the
wait.
Lagrange multiplier.
I'm sorry, can you just say that one more time?
Okay, so if you go in a very simple situation, like even in finite dimensional, to answer the existence of a Lagrange multiplier, most of the time you require the functional to be non-degenerate, like the derivative to be non-zero on the constraint.
Oh, yes, yes.
So here you talk about the Lagrange multiplier. So my question was, is the constraint non-degenerate, or you have to do some brute force to do the existence of the Lagrange multiplier?
I think it is non-degenerate,
The constraint.
yes. Yeah.
Okay. And the last one is you talk about Morse theory. Is this functional verifying the Freedom property?
Wait, okay, I'm sorry. I'm a bit, I think what you're saying, at least in the finite dimensional case, is true, but I don't know about the,
No, for the finite dimensional case, that's to
yes,
say maybe that's a trivial problem.
right.
I don't look finite dimensional. My point is, if you want to do the Morse theory successfully, at least you should have a sort of Freedom property.
Yes,
It
okay,
may-
so I
No.
don't have that yet. So I can prove that these equations are elliptic.
Because the point is, if all the Morse index are infinite, there is no hope to do.
Yes, so that's one thing we would have to sort out. So it should be somewhat similar to what they do with J-holomorphic curves. But all those, so there's a lot of things that need to be proved, that the moduli space is a manifold, that we have to have some, so there's basically this, we have this section here, and we perturb in the direction of, so right now we perturb the embedding, but then we also have to write down some perturbations of, okay, so what we do is we start out with this SU3 structure, and then we actually invent a notion of a tamed SU3 structure. So we add two more forms, which is a separate SU3 structure, taming the first.
Mhm.
And then we have to perturb that, and you'll get some other sections in that direction, and you have to show that the Fredholm operator and all this stuff. So I didn't do that yet. That's what I'm working on right now. So
Yeah, good luck, because usually perturbation is used non-degenerate perturbation. Otherwise, it will be stuck to your.
yes. Now that Doan and Walpusky did do something very similar to this with associative submanifolds. And I think, so here, the issue is you just want to look, you can kind of consider everything on the G2 cylinder, and then you want these sort of T invariant G2 structures. So I'm kind of hoping I can sort of just tailor those results to help me out a bit.
Are there other questions? I will ask one, I remember. Oh, in the Calabi-Yau case where it's not Morse, but possibly Morse bot because of McLean's, have you thought about a Morse bot version, or has somebody?
Well, I asked Mike Miller about it, and he said he has a warning for me.
Ah, okay.
So, maybe. Seems like something I should think about.
Ah, one more.
Yeah, that's interesting about the stable forms. I was wondering if this stability has anything to do with the second variational formula of certain functional to be non-negative.
I'm not sure. I feel like there might be something about that in the McLean paper, but I'm not.
I see.
I'm not sure. So the one thing is this stability condition is entirely linear algebra, though.
I see.
So the stuff about, like, for example, torsion free and everything, that's, so you usually want to make the forms and their duals closed to get torsion freeness. Otherwise, you have all these torsion forms, which are kind of interesting in their own right, but so I'm not sure if that has anything to do with it.
Yeah. If we look at collaboration, it has something to do with the stability of area, because it's area minimizing due to the Stokes theorem.
Right, that's
Yeah,
true.
So
Yeah.
So I don't know if that is the same along the.
Well, I guess it is important. Yeah, I don't know. I'm not sure precisely.
Is there any perspective that finite dimensional can be extended to infinite dimensional, just like Morse theory? It started with finite dimensional, and then to loop space of geodesics, it's infinite dimensional.
I did think about that, but I don't know how to do it.
Thanks.
Well,
Last question. So if you have a sequence of solution of your constraint critical point, because
Yes.
here you write the constant gradient, okay? So, and the first question I asked you was whether the Pallas-Mail condition is true. And
Yeah.
you said it was not clear. Now, if you take a sequence of solution of the constant problem, exact, not almost, is it known the compactness or at least the blow-up formation? How do those sequence of solutions which are not controlled, how do they escape to infinity?
No, it's not known. And in fact, I think there is a bunch of work on that, and I think it's quite bad. I think there's some very interesting and bad things that happen, especially, for example, so at some point you would want to, I'll just talk about G2 because it's a bit easier. So if you have like a bunch of a family of G2 forms, and then you look at the associatives in there, and then you deform T, they can degenerate in some very strange ways. And so I guess the idea is that you would want to somehow count them with some weights or something like that, but no one really knows how to do it. So I think something similarly bad happens with special Lagrangians.